over those, so I apologize for that from the outset. But this goes over what I think the teams will need to know for mobility. And we're going to give you some of the inside baseball statistics here. Let's see. Oh, the dog is asking to go out. Hang on one second. Let me just yell at somebody to come get the dog. Sorry about that, bad timing. Okay, so we're trying to develop robots that are relevant to the moon. And so we have created regolith, or simulated lunar surface material, that simulates the physical characteristics of the soil, so that trying to drive in it should be similar to an actual experience of driving on the moon. So in order to simulate the lunar conditions, we have to think about the geology. Lunar soil is completely unlike terrestrial soil. And because it's so exotic, there is no lunar soil simulant that can meet every need. The dominant geological process on the moon is impacts from meteoroids and comets. And the larger impacts break up the bedrock and throw out ejectablankets, which is coarse sand and gravel. And then over a long time, the micrometeorites continually pummel the soil to wear down the rock into finer material, including a lot of dust. So lunar soil particles are very sharp and jagged. Unlike terrestrial soils, they never get rounded in the wind or the waves. And so they're very sharp and angular. You will notice that there are some spherical particles in that lower right-hand corner. Those are glass because the volcanic fountains on the moon have thrown out lava, which pulls into a spherical shape before it hits the surface. And if they're small enough, they harden before they land, and so they stay spheres. So there are some spherical particles, but it's mostly very sharp, jagged particles. The particle size distribution, this is cumulative. So 100% at the left side means that all the particles are finer than roughly 10 millimeters diameter. But then as you go down the scale to smaller sizes, you get to a 50% mark at around 60 microns or 70 or 80 microns. That means 50% of the soil is finer by mass. 50% is finer than about 60 to 80 microns. And then there's a significant fraction of really fine dust, like 10 or 20 microns and finer. And that fine dust creates a lot of cohesion in the soil. Now, lunar soil is not all the same. Some is mature, some is immature, and some is in between, we call submature, depending on how long it sat on the surface getting pummeled by little micrometeoroids. So the mature soil is finer, the immature soil is coarser. But the vast majority of soil on the moon is really mature. And so what we're trying to simulate is the mature type, which has a lot of fine powdery material. Lunar soil does not flow well. The particles, because they're sharp and angular, they have high friction, and because of the high quantity of dust, there's a lot of cohesion. And sorry, the dog's howling in the back. And because of low gravity, it's even worse. So we've done experiments, and the lunar soil does not flow well at all. The simulants tend to flow better than the lunar soil does. BP1 is actually one of the best simulants. BP1 is what we use in this competition. It's one of the best simulants for replicating the flowability of lunar soil. And when I say it doesn't flow well, what I mean is you can put it on a plate and tilt it way up at a steep angle, and it'll just sit on that plate. So if you design a dumping system that dumps the soil and you test it with sand from the beach and it works, well, it may not work with lunar simulant, because you can tilt that thing 70 degrees and it might still not come out. Okay, so cohesion, there's a lot of cohesion in the soil. Between 0.1 and 1 kilonewton per square meter, or that's kilopascals. So between 100 and 1,000 pascals of cohesion, which is pretty significant. Beach sand has about 0. So if you plot the normal stress versus the shear stress at the point that the soil begins to slide, and you do it at different values of normal stress, you'll find that the points fall along a sloped line that has an intercept. That intercept is the cohesion. And then the slope is the friction coefficient. The tangent of an angle is defined as the friction coefficient. So that angle is called the friction angle. Lunar soil looks like around this range. It varies quite a bit depending on the maturity and other factors. But we've measured lunar soil. We know the cohesion is around in this range, and the friction is a slope similar to what you see here. But here's an important point for mobility. If you repeat the experiments using different compaction of the lunar simulant, you get different results. So these are a series of tests where the soil is 0% compacted all the way to 100% compacted. 0% means it's as fluffy as you can get it, more or less. 100% means it's as compact as you can get it. And on each point, the x-axis is the cohesion and the y-axis is the friction angle. And you can see the cohesion and the friction angle both increase with compaction. So eventually, as the soil gets compacted, it becomes extremely strong and hard to move. On the other hand, as the soil gets fluffed up, like your wheels churning it and fluffing it, it loses friction angle and it loses cohesion, and it becomes weaker and weaker as the wheels shear the soil. So that's very important to understand. As you're driving, as you're shearing the soil, you are changing the properties of the soil, and that is unavoidable. Wheels will always shear the ground beneath them. And so as you drive, you always change the property of the soil that you're driving on. And the more you shear it, the worse it gets. Okay, so now the moon is generally very compacted. I don't want to go through all the data points here, but on the crater rims, it tends to be fluffier. The rims of fresh young craters can be very fluffy soil. Also, when you measure, I don't want to go through all the details here, but when you measure the density of the soil or the compaction as a function of depth, then you find out there's generally a curve. It's not a perfect curve. Like everywhere you go on the moon, it could be pretty random. Like you can see these curves go back and forth, back and forth. It's because the layers of the soil, you could have hard on top of soft, on top of hard, on top of soft, depending on the history. But in general, it averages very fluffy at the surface and getting very compacted asymptotically, reaching almost 2 grams per cubic centimeter bulk compaction at depth. But the surface, to reiterate, the surface is super fluffy, and this is where your wheels are interacting. So we have to drive in this loose, fluffy material. And look at the x-axis, that's 100 centimeters of meter depth. So we care about the top 20 centimeters. And so this is the range of compaction we're dealing with, very fluffy soil up in that range. Okay. So now I'll skip over this. I'll just say briefly, the polar soil, we have evidence is maybe fluffier than the equatorial soil where we went during Apollo. There's scientific reasons for that, which we've been studying. Okay, so let's go through some robots. I want to just go through real quickly the wide variety, diversity of robots that we see. Oh, well, first of all, I'm going to talk about the regolith a little more. Okay, so this is an example of where a vehicle was driving and digging as it drove, and you can see the steep, the vertical sidewalls in the soil. This is dry soil, and yet it maintains a vertical slope, and that's because of the cohesion. So our simulated lunar soil has a lot of cohesion. So this is us raking the soil. We try to fluff it up because when it sits there in Earth gravity overnight, the air that's in the soil tends to come out, and the weight of the soil makes it get more and more compacted. And it was getting too compacted. And so every morning we would go in there and rake it up to fluff the surface again to make it more like the moon. I heard that this year they got the soil so dry that it was very fluffy. So I don't know if we still need to rake it. But just to let you know, we try to keep the fluffiness appropriate to match lunar conditions. Okay, I was talking about the competition, about the creativity, the spirit of the students. This is an interesting robot. Doesn't look that well designed, does it? But This was from the Czech Republic. Their robot got lost in shipping. And so during the competition, they started from scratch and built a whole nother robot using donated parts and duct tape and Coke bottles. And it actually worked. I mean, it moved. It didn't successfully dig, but they were actually able to drive it. And so that counted as a win. Okay, so we do a lot of investigation. The judges are there taking notes. You see, we got clipboards. We're not just taking notes for scoring the robots, but we're also taking notes to study the robots. And and we've kept this data secret, but today I'm going to give you some of the data. Okay, so there's a lot of different designs of robots just to show the wide variety. There's dual robots. There's another set that I think they actually had 3 robots in their set. Stacking robots, robots that have different kinds of suspension. You see there's a rocker system on 2 of the wheels, a different kind of suspension here, 3-wheeled robots, tracked vehicles, robots that drive on screws, metal treads, rubber treads, all kinds of different 3D printed treads. These are wheels that were made out of salad bowls bolted together. Angular chevrons, straight grousers on the wheels, different track systems. Now I want to tell you, it's very difficult to get a track system to work in this soil. And the reason why is whenever you turn, I'll show a picture of that soon, but whenever you turn it with a track system, you scrape the dirt and that dirt goes into the wheel system. I'm going to have to pause a second to let that dog out. Just hang on 1 second. Okay, I'm back. I apologize for the delay. Okay, so track systems, when you steer, you inevitably scrape some dirt between the wheels and the track. And then that, as you drive, that dirt gets pulled between the wheels and the track. That tensions the belt. It puts side loading on the wheels, the wheels at the 2 ends. It side loads those axles. And it can lift the tracks completely off the wheels. We've seen tracks break under tension. We've seen the wheels stop turning because of the side loading on the axles. And also you've got so many little joints in those treads that get dust in them, which builds the friction. And so it's possible. There are some teams that are committed to treads and they have made good tread systems, but it takes a lot of engineering for a small vehicle to work successfully. We asked Eric and we asked the other Caterpillar people, how do you design a system to work with treads? Because the competition, all the tread vehicles were failing. And so we asked Eric and the others at CAT, and they said, well, for one thing, it's a lot of iron or steel and a lot of horsepower. And so that dust and dirt can get pulled right into the wheels and crushed to powder and then extruded. So if you have a big enough vehicle with enough power, you can just power through it. But on a small vehicle like this, that's not really an option. And so that's partly why it's so hard. But even so, Caterpillars, they told us that their systems, their tread systems are very highly engineered systems of systems. There's a lot to it. Okay. But you see, there's different examples of different kinds of track systems with the drive wheel above the surface. Here's I think we're going to talk about, no, it's still talking about wheels. Just more examples of different kinds of treads. This was a system that was designed with very, very wide wheels, so it floats on top of the soil instead of digging down into the soil. And it's a different approach, a different tactic. You could have a vehicle that has narrow, tall wheels that digs down in deep to the more compacted soil, or you could have one that's very wide and floats on the top. Here's one with rounded wheels. This was designed copying Mars rovers. They tried to design it so that if you hit a rock, it would roll off the side of the rock. We had a team that had very non-functional wheels, so they ended up putting frisbees, just to show you a little bit about the creativity. Okay, different steering methods. Steering is important, it turns out. So this is an example roboticists call this independent explicit steering, because each wheel can be turned independently and the vehicle has a lot more degrees of freedom in its ability to move around. This is tank steering, and you see I mentioned when you're steering with a track vehicle, you scrape dirt in the side, you can see the pile of dirt that's building up right there. And that dirt, as you're turning, is getting pushed into the tracks. So that's one of the challenges of track systems. But even wheel systems, if you have a system without any sort of active steering, then on a smaller scale, as you turn, let's say it's called skid steering because you're skidding. And so the way you steer with that kind of a system is you simply turn the wheels on both wheels on one side of the vehicle at a higher rate than the two wheels on the other side of the vehicle. And that causes one side of the vehicle to move forward faster, which rotates the vehicle. But as you're doing that, the vehicle is rotating around its center line, around its center of gravity, at the same time that it's translating forward. And what you're doing is you're skidding your wheels sideways, left and right, across the soil, and that digs dirt into the sides of the wheels, which creates additional friction and resistance to travel. And this could cause what I call an initiating event. So whenever a vehicle gets stuck, there's usually an initiating event that precipitates a chain of reactions that ends up being stuck. So I'll say more about initiating events a little bit later. Okay, so suspension systems, that one was rigid. That one has rockers on the left and right side for differential averaging. There can be suspension, like there's spring systems in the tracks here. This one had spongy wheels, which was like putting suspension in the wheels themselves. Digging systems, that's a snowblower, that was a scraper. This one used bags to scrape along the surface, augers, bucket loaders, scrapers, front and back, bucket wheels, wide variety. Okay, there's an example of getting stuck, by the way. The initiating event on that one was they hit the wall. Okay, so this was carbon fiber wheels that were digging wheels, so the wheels would dig as they drove, which was creative and unique. But if your key challenge is not getting stuck, then you might need to focus on just mobility for your wheels. You're taking a risk if you want to try to put more requirements into your mobility system, but it's doable. Okay, bucket ladders. Okay, this was a general talk on the robots. So talking about dumping, you can see that that angle there looks like about 45 degrees, but even so, it's not really enough. And the soil can hang on the robot. And so teams would have to try to jolt forward and back to get the soil loose. A tip for you is just use a steeper angle. Okay, steep angles are good. This angle here, this is not that steep of an angle. If you look inside the box, the soil is at a really steep angle, but if you look at the side of the box, you can see the bottom plate of that box is at a very shallow angle. And so that soil is mostly not coming out. It's mostly sitting inside that bucket, not sliding out. Okay, you can use buckets to reverse rotate to dump it out. Talked about chassis. You can use 2x4s or carbon fiber or anything in between. This team used magnesium. This team, you might recognize this. This is University of Alabama. I was mentioning that some teams use very sophisticated navigation systems and guidance. Sensors to avoid hitting the wall too hard. Okay, let's talk about getting stuck now. Okay, this robot was made to float on top of the soil, but even though it was designed for floating on the top, it still dug in and got stuck, which just emphasizes the point that I firmly believe there is no such thing as a vehicle that's immune from getting stuck. What you do is you design for margin. You want to put margin in there so that when you operate it, there's less chance of making a mistake and causing an initiating event, which results in getting stuck. But even with a perfectly designed robot, it depends how you drive it. Okay, now for an autonomous robot, how you drive it is part of the design. So and I think in principle, you can have a robot that's so well designed with autonomy so it becomes immune from getting stuck. But part of that immunity is the way it's driven. Okay, just the mobility hardware itself is not capable of giving you a robot that's immune from getting stuck. But you want to design it for the most margin you can get. Okay, so I'll talk about how to get margin. But this is what happens. You look at the wheels and the wheels dig in, they fluff up the soil. The soil becomes like liquid because it's so fluffy, low stress, shear strength, low friction, low cohesion, and it just fluffs the soil up and it digs a deep hole. And then to get out of that hole, that robot has to drive uphill. So it's got to lift its own weight up, several centimeters while trying to shear the soil on the uphill. And it just can't do it. The sheer strength of the soil is not enough. Here's another little trick to remember. The maximum traction that you can get on your vehicle is not a function of the vehicle. It's a function of the soil, because the soil is going to shear, and whatever the shear stress is, that in your free body diagram is the maximum amount that can transmit in from the boundary to your vehicle. And so it's a function of the soil properties. And if the amount of traction is not enough to lift your vehicle out of a hole, then you're not getting out of that hole. So you want to avoid it starting in the first place. Here's a vehicle that was really well designed, tall wheels, but unfortunately they drove into a crater. And once they got in the crater, they're not under ideal driving conditions. You notice that left wheel is slightly raised off the ground now. So they're trying to drive on two wheels that are outside the crater, plus one wheel it's only getting traction in the upward direction to pull itself out of the crater. But if you can't drive on a reduced number of wheels, then you can't get out of a situation like this. Here's another one. This was like the worst case. They got into a crater and started trying to drive out, but the more they drove, the more they dug the hole. And here's another example, a wheel buried up to its axle in the fluffy soil. Here's one. This one was Nebraska. I remember when this happened. They tried using their digging bucket to provide additional traction to pull forward to get out of the hole. But even with the digging bucket, they weren't able to get out. After they removed the robot, we took pictures because we wanted to study this to understand why our vehicle is getting stuck. So I tweeted this picture and I said, yeah, we're still trying to understand what this means. Somebody edited my picture and sent it back to me and said, I can tell you what it means. So that's what it means. It's like, oh my goodness, we're stuck. But you see, here's a vehicle they were trying to turn. As they were turning, they were scraping the dirt sideways because they did not have any active steering. It was skid steering. Now, skid steering is okay. You can make it work, but it's one more factor that reduces your margin. Okay, so when you're trying to drive with skid steering, you are shoving the dirt sideways a little bit. And that provides extra resistance to the motion you're trying to induce. You loosen the soil begins to get fluidized, and now you can see there's semicircles of fluidized soil flowing down into the wheels. Okay, so I'm going to just mention this one real quickly right here. This one we gave, this, if I recall, was Case Western, and we gave them an award that year for their wheel design. And I want to say that you don't have to have a fancy wheel design like this. It's just one more thing you can do to build margin. I'll say that over and over again. But see, what this wheel did was, instead of shearing the soil and fluffing it, as it drove, it compacted the soil. It had these inwardly curved surfaces with spikes. So as it drove, it compacted the soil, and then the spike would push off of the freshly compacted barrel of soil that it had just compacted in place. So it strengthens the soil and uses that to get torque or traction. So that was a pretty innovative design. I don't know, it probably has downsides as well, but I just wanted to point out that you got to think that it's an interactive system. The soil is part of your engineering system. And so you got to take the soil and how you're changing the soil into account. And then dust, generate a lot of dust. Okay. And then I'll skip over some of this. Okay. So we started taking data. After the first couple of years, I said to the others at NASA, why are we not collecting data on this? This is amazing data. We've got 50 robots being hand delivered to NASA for free. We get to study them for a week and collect data. And if we built a robot internally, it would cost us $1 million. So this is like $50 million worth of test experience. We ought to collect data on it. And so we started keeping statistics, like how many wheels on each vehicle, how many different steering methods, Ackerman steering, screw steering, independent, explicit, suspension systems, do they have something active or not? The methods of dumping the soil, the mining methods. We looked at how they changed year by year. So we started keeping detailed statistics. One of the things we did was we started trying to rate the vehicles on how well they could avoid getting stuck. So it was a 5-point scale. A 1 means it got stuck very early and never showed any possibility of being able to drive in the soil. In the early years, a lot of robots were like number 1. They just could not drive. But number 2 meant they had a very tenuous ability to drive. They were usually on the edge of getting stuck, and they possibly did get stuck after some initiating event. By the way, I'm going to pause and say, I wasn't at the competition for the first time last year, other than just speaking at the dinner. And I understand it was a rough year. A lot of vehicles got stuck. And I think I've been told there were 2 reasons for it. Number 1 was the soil was a lot drier and fluffier than historically it had been. But number 2, and this is really crucial, is because of COVID, we had some gaps. And I think a lot of teams are starting over, and they didn't get to pass the heritage down from earlier teams. And so that heritage is crucial. We learned that in the first few years of the competition, no vehicle could drive. Very few vehicles could drive. In the first day, the first round of the competition, no teams successfully mined any soil. And they had to have an additional extra round in order to have a few teams successfully mine. So it definitely gets better, but you've got to build on the heritage of what's been come before. So that's why we're doing this talk today. I'm trying to pass on the heritage of many years of experience so that we can jumpstart the process of teams getting going again after this COVID lockdown. Okay, so a 1, it can't drive. 2, very tenuous driving ability. 3 means reasonable ability to drive, but still there was significant wheel slippage or poor turning. You could just see that the vehicle was struggling a little bit, and there were signs that getting stuck might happen. It doesn't necessarily get stuck, but you think it could get stuck. Number 4 means it drives with only modest wheel slippage, easy turning, no great signs of getting stuck. And a number 5 means the vehicle displays complete dominance over the regolith, no slippage, easy turning, the robot owns the soil. So it's a qualitative scale, but when you are in the arena looking at 50 robots day after day, it's pretty easy to give them a rating 1 through 5 like this. Okay, so Now here's what we learned. The first time we did this, we thought, okay, so what we're going to see is that wheels that are bigger wheels don't get stuck. But when you look at the rating 1 to 5 and you look at the wheel diameter and plot them against each other, there was no correlation. No correlation at all. That shocked us. Okay, what about wheel width? Okay, surely the wheel width. Nope, no correlation. Wheel width had no correlation to drivability. We were shocked. Okay, what about gear ratio? Again, no correlation. What about output torque of the motors? No correlation. No correlation at all. What about the wheelbase aspect ratio? Because if the vehicle is really long, like a dragster, then turning skid steering is even more difficult because it has to, rotate a longer wheelbase forward to aft around the center of gravity. But no correlation on wheelbase aspect ratio. Oh, so we were shocked. We couldn't find any parameter that correlated to better drivability. Well, this is the same is true in biology. Snakes, giraffes, tigers, ostriches. If you look at giraffes and ostriches, you think, okay, long neck makes it survivable. But then you look at snakes and you're like, nope, doesn't have a long neck. It doesn't even have a neck. All of these different species are very adept at survival, but you cannot look at the individual body parts alone to predict their survivability. Only the total package can correlate to the survivability of any of these different species. And our data shows the same thing is true of regolith drivability. The individual components cannot predict drivability. Only combinations of parameters correlate to good drivability. So what we did was we dug into the data and we tried to come up using a purely empirical method to come up with some combination of the parameters that would correlate to drivability. And so what I'm going to show you is an equation based on 7 parameters: wheel diameter, wheel width, motor output torque, gear ratio, steering, suspension, and ground clearance. These parameters are weighted by different exponents, and we chose the exponents empirically. Like what I did was I would increase it until the correlation started getting worse, and then I'd make it a little lower, and I'd find the sweet spot. And I did that for every parameter until I got the maximum correlation. And this does successfully correlate to good drivability. And we know that there's further improvements possible if we include the wheelbase aspect ratio, but I didn't include that here. So this is what you get when you plot this metric versus drivability rating. It's really strong correlation, okay? And so if you have a robot that scores up at around 1 million points or higher on this metric, then that vehicle will probably have a 4 or 5 rating on the drivability scale. Now, there were some outlier data points that we understand. We knew what was going on those vehicles, why they didn't drive well, and it didn't have anything to do with these 7 features. So there is some scatter in the data, and we think that with more research, we could improve this equation. I just wanted to say, don't be put off by the scatter in the data. We think we have real meaningful correlation here. Okay, so, and here's why heritage of a team going year by year is really important. You see, we never shared this equation. I'm going to show you the equation in a minute. We never shared this with any team. And yet, look at the average score averaged over all the robots from 2016, and then look at the average score averaged over all the robots for 2017. It increased by a factor of 30 from one year to the next. And this is what we saw happening. Every year, the robots got better and better and better, which is pretty remarkable, because if you don't have access to the data, and if you just go around and you look at all the wheel diameters, you're not going to see any correlation. So somehow, in the magic of this competition, the teams engineered it and figured it out and made the robots get better every year. And so, like wheel tread, I'm going to show you that a wider wheel tread is more beneficial, but but if you just look at wheel tread alone, you won't see that correlation. But look, from 2015 to 2016 to 2017, the wheel tread area was increasing year by year, which means it was moving in the right direction, even though the individual component statistics can't prove this. So how was the competition able to do this? Well, we think it was a well-designed environment for rapid evolutionary advancement. It was a survival of the fittest type program because there were rewards for success. There was descent with modification because teams kept returning with modified robots or new robots built on the heritage of what they already learned. There was a short reproduction cycle, 40 to 50 new robots per year. And there was significant trial and error. But it was also a guided evolution process. There were like 500 young minds every year creating this hive mind that was smarter than any one individual, we think. And there was the equivalent of genetic engineering because teams were using logic and math to design the robots. So it wasn't just a survival of the fittest type thing. There was gene transfer because teams would copy each other and share ideas. And there was a hot box environment that had positive social dynamics to encourage collegial sharing, but yet with competition. And we think this is a successful combination of guided and unguided exploration of the parameter space. So here's the equation. And you can write it down or look at the video later to get it. But pi times the wheel diameter times the wheel width. If you recognize your simple geometry, that equals the area of the tread on your wheel times the number of wheels. Okay, so that's the total tread area times the gear ratio. We didn't include motor torques in this because we didn't have enough data on the motor torques. But so anyways, just looking at the gear ratio, higher gear ratio is better. You know, gearing down from the motors to the wheels. Suspension plays a role. So now suspension is a rating from 1 to 3. 1 means it's a rigid body system. 2 means it has some kind of simple suspension. And 3 means it has really good suspension. And it was just a qualitative score, but we didn't have enough vehicles with anything other than rigid body. So this was the best we could do. But the maximum correlation is that to the 1/2 power, or the square root of that metric, 1, 2, or 3 times this, taken to the square root. Okay, and then the steering metric to the 0.66. Now steering got a 1 if it was skid steering, and it got a 2 if it was anything other than skid steering. Independent explicit or Ackerman or anything that was more sophisticated will get a 2. So raising that to the 2/3 power gave us maximum correlation to drivability. And then the aspect ratio of the vehicle. Now we defined aspect ratio as the longest dimension divided by the shortest dimension. So this number is greater than or equal to 1 by definition, but that to the minus 0.4 power. In other words, it's inversely correlated to aspect ratio. Now, when you plot that equation versus the drivability, that's where we got good correlation. So what we think you could do, this is a hypothesis, it hasn't really been tested, but it's based on data, is that if you take that equation and calculate it for your robot, and if you get a value of like 1 million or higher, then your robot probably has a lot of margin in the drivability so that the chance of doing an initiating event to get stuck is a lot lower. So you can avoid getting stuck. Okay, I wanted to mention initiating events. This is just going to flip through pictures of the competition, show the wide variety of vehicles. But so an initiating event could be anything that's non-standard, which causes the wheel to shear the soil more than normal. And in case I don't remember, I need to come back and mention wheel diagonalization. So an initiating event could be anything. If you're driving along and one of the wheels bounces on a rock, that little jolt could cause your other wheels to slip a little bit. And that little bit of slip could shear the soil, which loosens the soil and makes the soil weaker. So then the wheel slips even more and it runs away at its self-reinforcing feedback. so it goes out of control, and you end up with a wheel that completely loses traction. So it could be something like hitting a rock, or driving over a crater, or hitting a wall, or something about the way your mining mechanism, not coming all the way out of the soil before you try to drive. We always see some little initiating event. Now, I wanted to mention wheel diagonalization. Sometimes the initiating event is simply getting started. You're at a standstill and you need to start driving forward. Now, if you think about it, your computer is going to start sending more current to the motor controllers, or the motor controllers are going to start sending more current to the motors. And it increases the current. The vehicle's not moving yet, so it increases the current a little more. Vehicle's not moving yet, increases the current a little more. Well, now the torque on the wheels, it should be the same on every wheel, but the strength of the soil under every wheel is not the same, because the soil is very random. And so one of those wheels is sitting on top of soil that's weaker than the other three wheels. It's inevitable, okay? So as you're increasing the motor torque, inevitably one wheel is going to be able to turn before the other three wheels start to turn. And as that wheel turns, it's going to shear the soil, but one wheel turning is you haven't increased the torque enough to get forward motion. And so the vehicle is not moving forward. It's simply one wheel turning in place. And that one wheel turning shears the soil, loosens the soil under the wheel. And as a result, you end up with a hole under the wheel. Now, if you think about the center of gravity of the vehicle, if the center of gravity is near the cross point of those four wheels, draw the two diagonal lines. If the center of gravity is near the center of that X, and you've now got a hole under one wheel, it doesn't take a lot of upward force from the diagonally opposite wheel to push it up a little bit so the vehicle rotates on that diagonal. And so what happens is the diagonally opposite wheel lifts itself off the soil and reduces its normal force. And when it reduces its normal force, that reduces the shear strength of the soil under that wheel. And so that diagonally opposite wheel begins slipping, and it digs a hole under it too. And you cannot believe how many times we saw this happen. In the first 2 years of the competition, we saw it happening over and over with diagonally opposite wheels digging holes, and then the vehicle is stuck. Now, so here's the deal. You almost can't prevent this. There is a way to prevent it. I'll mention it. There are multiple ways to prevent it, but you got to know about it and think about it to prevent that from happening. If you don't prevent it and you get wheel diagonalization, you now have effectively a two-wheel vehicle, because two of the wheels, one, let's say the right front and the left rear, those two wheels no longer have good traction on the soil anymore. And so if your vehicle has enough margin in its torque and its gear ratio, then you can drive forward on the remaining two wheels and get out of that situation. But if you didn't design at least 100% safety margin in your mobility system, to go from four wheels down to two, that's, if you don't have 100% safety margin, then be able to drive on two wheels times 100% more would be the four wheels, right? So four wheels has double the amount of traction that it needs. If you didn't design to that much margin, then once you've got wheel diagonalization, you're stuck. You can't get out. And so we saw this happen over and over and over. We were amazed, why does this happen? Well, I just gave you the explanation why. It took us a few years to figure that out. Now, there are some ways to avoid that. One way to avoid it is simply have a lot of traction so you can drive on the remaining two wheels. The other way to do it are a lot of torque and gear way down so your wheels turn slowly with huge power. Another way to do it is to have some sort of mechanical or electronic linkage between the front and rear wheels so that the rear wheels cannot spin at a higher rate than the front wheels and vice versa. So you can either have chains that connect the front and rear wheels together mechanically, or you can have some sort of encoders on the wheels with an electronic feedback to essentially chain them together in the electronics. That will entirely prevent wheel diagonalization. And we've seen teams do it both ways. Another way, maybe you don't chain the front and rear together, but having really good slip control so that if a wheel begins to slip and if the torque goes down and it's maintaining rotation, then you need to back off the torque on that wheel and increase the torque on the other wheels. So having really good independent wheel control is another way to avoid that diagonalization from happening. Okay, so we did see correlation with suspension. We have not had a lot of different vehicles with different kinds of suspension systems. So the most we can say is that there is at least some crude correlation. That makes sense because if you start to shear the soil under a wheel, then the suspension will push the wheel down to maintain traction under that wheel. We do see some correlation with steering. That makes sense because if you can turn your wheels and steer, then you've got less side loading on the wheels, less piling up the dirt, and less chance of causing one of these initiating events. It just reduces the rolling friction if you can turn the wheels into the direction of travel. Also, I didn't mention, but ground clearance is another important one. Some vehicles get stuck because they dig in and maybe they could have gotten out, but the chassis hits the ground before they have a chance to finish digging their way out. So having more ground clearance gives you more margin to pull out of a hole. Also, if you accidentally drive over a rock, having a higher ground clearance can help you avoid one of these initiating events where you bounce on the rock and then the wheels slip a little bit and then it induces a runaway series of events. So ground clearance was also important. Okay, I think I went over, I think I went over all the things that I wanted to talk about, but I'd be glad to take questions.
Thanks, Phil. That was awesome. Anybody got any questions?
I got a question for Phil to comment on. So the competition in May is going to now be held at University of Alabama, and that simulant is a little bit, it's different than BP1 at Kennedy Space Center. And my recollection of it from 19, and I don't know how good your memory is from 19, Phil, when you were there as well, but I think that simulant is a little bit more forgiving than perhaps BP1 is. But how would you expect? I guess I'm expecting and looking for you to your input on this. I'm expecting that though this general guideline and thought process is going to hold true for the other simulant at Alabama.
Yeah, so I did get the experience 2 years ago where I came, or however many years ago it was, where I came up to Alabama and helped judge that competition. And it is a good simulant. You know, it does display a good simulation of lunar soil in general. But the ways that I would say it's a little different, if I'm going by memory here, is I think it can get compact with depth at a shallower depth. Lunar soil can tend to stay fluffier for a deeper thickness of fluffy material. And if I recall, the crushed limestone can settle down. And so at a smaller depth under the surface, it can be pretty compacted. Ken, please speak up and correct me if anything I say is wrong. Also, there is a large fraction of dust in that material. It's very dusty. And so some of the shearing behaviors are the same. But I would say quantitatively, it's inevitable that there's going to be some differences. So quantitatively, the shearing and the cohesion are going to be different. But qualitatively, you're going to see the same types of behaviors.
Yeah, I can agree with you for the most part, Phil. You're the regolith expert, but when we test on our own in our own simulant here, and then we go to Florida and test in the BP1, we don't see significant differences other than maybe environmental conditions that's really difficult to control, like the amount of humidity. But we see very similar performance of our robot on campus as we do in the BP1. I do think it compacts pretty heavily. I know in 19, the pit judges made a specific effort to make sure that they fluff the surface a little bit more than they do in Kennedy. I think maybe because, like you said, the fluffiness doesn't extend quite to the depth of the BP1. But in general, we don't see huge differences between how we perform mobility wise on campus versus the BP1.
Okay, yeah, that agrees with what I recall. Thank you.
I had a question for you, Phil. Do you see a correlation in mobility to mass of the rovers, the overall weight and mass of the rovers?
That's a great question, and we never got that data. Now, NASA collected that data. It's kind of funny though. It's an example of the left hand and the right hand not talking to each other. The judges who weigh the vehicle during the check-in, they've got their records, and then I was collecting data by going around talking to the teams, and we didn't have a scale with us when I did that. So we never merged our data sets to get the mass of the vehicles. Based on what I've seen though, I'm not sure if there would be much correlation. I mean, a vehicle that's heavier, you're going to dig into the soil more, whereas a lighter vehicle is going to float on the surface. In general, smaller vehicle, I can say about size rather than weight. In general, my qualitative experience is that smaller vehicles have a harder time driving because there's a certain thickness of the fluffiness. And if your vehicle is, 10 times bigger than that, then that fluffy layer it's just an annoyance. You just drive over it, you ignore it. But if you've got a vehicle that's the same height as the fluffiness and you sink into it, then you can't drive. So that's a very simplistic argument to say that there is a length scale that matters. And this is partly why larger diameter wheels seem to do better. But we have seen vehicles that were designed to float on top of the soil. We've also seen vehicles that were designed to dig in. Like you may recall, West Virginia several years had a vehicle with huge gear ratio, huge motor torques. They had really big diameter wheels, but they were narrow wheels. And those wheels would dig down into the soil like 8 inches deep, and they would just power through and drive out of their holes every time. And it was actually a strategy. By digging these deep holes around their wheels, they were getting more traction so that they could push their digging bucket deeper. So you can design a vehicle to dig down in, or a vehicle that can float on top, either way. Now, we used to look that year, I remember looking at West Virginia going, wow, that vehicle will never get stuck. But you know what happened? The last day of the competition, it got stuck. And so that was one of the experiences that led me to believe that there's no such thing as a vehicle that is immune from getting stuck, apart from how you drive it. So even the best designed robots can dig a hole and get stuck.
So one more question, Phil. Since skid steering seems to cause quite a bit of problems with whether it's wheeled or whether it's tracked, a lot of vehicles that use skid steering seem to have problems when they're doing their 0-degree turns. Is there a significant advantage in your experience of having some form of articulated steering to avoid those problems?
Yeah, so it did show up in the data. If I can find the see, in this combination of 7 features, one of those is the steering, and the R² value that measures how good of correlation was maximized when we used 0.66 power on that steering factor, and the steering was either a 1 or a 2. one meant skid steering, two meant it was something better than skid steering. Now that we couldn't come up with a better equation than this because we didn't have enough data points with articulated steering. But anyways, maximum correlation does take into account articulated steering. If we didn't take that into account, the correlation to drivability would not be as good. So speaking from the empirical data, the answer is yes. The steering does appear to play an important difference, make an important difference. Qualitatively, I'll say that I agree with that. Now I'll also say this. We're looking at empirical data, so correlation does not equal causation. It could be that the teams that did articulated steering were the teams that had more experience, and they were more confident, and they were able to go for the next level, whereas teams that were younger and just starting out couldn't go for everything in their first year. So it could be that the teams that put steering in were just better, building better robots overall anyways. So we really can't tell for sure, but qualitatively, I know from watching the vehicles operate, anytime you're scraping dirt, then you're creating conditions that could cause you to get stuck. Anytime that you're not scraping dirt and the wheels are turning cleanly, then you've got a much better chance of avoiding getting stuck. So steering qualitatively definitely is a good choice. But also, I'll say one last thing about that. The key word here is choice. You're making engineering decisions. Part of engineering is economics. You can't afford everything. And so maybe you can't afford a suspension. Maybe you can't afford to do steering, but you've got to make choices to design the best vehicle you can with the time and the money you've got. So steering is one of the options. Suspension, something more than passive or rigid body, that's an option. Those are tools that you could choose to use to get more margin in your vehicle. You don't have to choose those tools. You could take another approach. So
I think that's an important point, Phil, because of, it's a trade-offs, right? And it's cost, but it's also perhaps time, right? Because suspension and steering is going to add complexity that you have in your design that you have to work through, et cetera. So
that's right.
I've got a clarification question, Dr. Metzger. When you talk about the immunity to get stuck being maybe, or like the key to that being how you drive it, are you referencing skid steering and articulated steering, or is there something else that you're kind of referencing there?
I'm sorry, ask again. I didn't follow completely.
When you're talking about, you say there's no robot that will never get stuck. Perhaps the only way to solve that is the way you drive it. What are you referencing there?
Okay. So the way you drive it means don't run into rocks, don't run into craters, don't run into the wall. Don't suddenly torque the wheels from 0 to 1,000,000 in 1 millisecond. Slowly start to increase the torque so that you don't spin the wheels and shear the soil. Don't drive too fast, out of control that causes you to skid and have an accident. So just cautious, general, good, solid driving to avoid disturbing the soil under your wheels too much. That's what I meant by that.
Gotcha. Thanks.
And it's really important point. We've given this information to NASA for the design of NASA rovers. I was on a Tiger team for the Viper rover. Well, it was called Resource Prospector mission way back. And they had a Tiger team to review the design of the mobility system. And so we actually took the data from the robotic mining competition and gave this to the engineers at JPL and at the Johnson Space Center to help guide the design of the lunar rover. So, but we tried to make the point that Oh, and let me just say, they were resistant to some of this. They didn't want bigger wheels. They didn't want, this or that, because of various philosophical commitments that they had to how you design a rover. And so we tried to make the point that every little compromise you make, you're reducing your margin and you're making it more difficult for the driver to avoid getting stuck, because ultimately it comes down to how you drive the vehicle. So every one of these parameters on this equation is a parameter that can give you more margin, so there's less chance of making a mistake while you're driving it.
Are there any other questions? So there's one question in chat, Phil. Someone is asking if you could make some correlations between what happens during digging and mobility.
Okay, we haven't tried to look at that, but we have seen teams use different approaches. Like some team, it depends on your mining system. If you've got a load haul dump system, a front end loader you use your wheels to drive that bucket forward through the dirt, then your mobility system is part of your mining system. And so you're generating the digging force with your wheels. There are other mining systems that don't do that. Like if you've got the Razor robot for NASA, that's got a front and rear counter rotating bucket drums. So the bucket drums create equal and opposite forces that cancel out. So you don't really rely on the wheels producing the digging force. You could also do a more vertical digging motion, and that's relying on the weight of your vehicle to provide the force to push the edge down into the soil. We've never seen it in the competition, but NASA has developed percussive or vibratory digging to vibrate and loosen up the soil, to fluidize the soil, to cause it to lose shear strength so that you don't need as much digging force. So there's a lot of different ways to do the digging, but in most of the ways, the wheels are going to have at least some role. Like even a bucket ladder where you've got this tilted chains of little tiny digging buckets, and the chains are rotating them around an ellipse. Unless it's directly vertical, if that bucket ladder is at an angle, and they usually are, then there is a component of force in the horizontal direction. And so the wheels are going to be providing a component to that digging force. So, anyways, you want to make sure that you can get enough traction to provide enough digging force. But then there's another issue. We have seen teams make the mistake of not fully retracting their digging system because it's a timed event. They're in a hurry. They start to retract it, but before it's fully retracted, they try to drive forward. And that causes one of these initiating events to occur. Your digging mechanism hits the ground, your wheels slip, and once the wheels slip, they start to shear the soil and fluff it, and then you have a chain reaction, and then they get stuck. So I don't know, I guess that's about all I can say about the interaction between the mining and the mobility at this point.
Okay, well, thank you very much, Dr. Metzger. I know we've gone over a little bit on the time that you dedicated to us, so we appreciate your flexibility with all that. And thank you again for your time. And as we get through the design process here and go through the design cycle, we may reach back out to you for your expertise in some other areas as well.
All right. Well, I'm looking forward to seeing this year's competition.
Thank you very much, Dr. Metzger. You take care.
Okay. Goodbye, everybody.
Thank you, everyone.